After a long hiatus, I have finally found time to upload new videos. Thank you for your patience. We are on a detour from AI with a series of videos on functional programming and monads. Please leave your comments below. If you like what you see, click the like button and subscribe to the channel. In the last video, we introduced the bare minimum of category theory to understand the mathematical definition of a monad. This video will connect category theory to functional and imperative programming languages. The next video will discuss how and why category theory and monads have influenced programming languages. In videos after that, I'll provide examples specific to various programming languages. I do assume you have some experience writing computer programs. In particular, you should be familiar with the concept of parameterized types, which are also known as generics or template classes. But for this video and the next, it doesn't matter which language or languages your experience happens to be in. Programming languages let you perform computations on data, which consists of different types of values. In functional programming languages, a type is thought of as a set of values. The set may actually be infinite. Of course, limitations on a computer's memory and lifetime will impose practical bounds on the data it computes with. Every programming language recognizes simple types for characters, integers, and floating point or real numbers. It doesn't matter whether the language is functional, imperative, strongly typed, statically typed, or dynamically typed. It is possible to combine simple types to create new composite types. In functional programming languages, types can be conjoined to create a composite type that includes multiple values of those types. The classic example is the combination of two real numbers to represent x and y coordinates on a plane. Types can also be disjoined to create a composite type that has alternative type values. Many languages have enumerations or unions, which are a kind of disjoint type. In fact, a type itself might be considered a disjunction of values, each of which is of its own type. The classic example is the Boolean type, which can either be true or false. You can define a composite type in terms of itself as one of the following: a simple type, a composite type disjoined with a simple type, a composite type conjoined with a simple type. If you watched the last video, you may have noticed the continuation of a pattern here. The difference is that we are mixing two ways of composing types, conjunction and disjunction. We also don't care about the order of composition. This tells you what a composite type even is, but make no mistake, functional programming languages do allow you to define a specific type in terms of itself. For example, a list of integers can be defined as a single integer or a single integer and a list of integers. Using this definition, you can build a list of integers of any length. You may have had the experience of defining a binary tree data structure, where a tree is an integer or two binary trees. Again, this allowed you to build a tree as deep and as wide as you want with integers at the leaves. A function transforms one value, called the argument, to another value, called the return or the result. We sometimes say it maps the argument to the result. In general, the argument and result could be of different types. In this video, I'll write f:(x) right arrow y to refer to some function f that maps an argument of the type x to a result of the type y. In imperative programming languages like Pascal and Fortran, functions cannot be assigned to variables or passed as arguments to other functions, at least not directly. Functions and values kind of live in separate worlds, and it takes unnatural effort to bridge them. This is part of the reason there's confusion about monads. You might be able to implement a monad in an imperative programming language like Pascal or Fortran, but you would have to introduce a lot of complexity because functions and values live in their separate worlds. In functional programming languages, on the other hand, functions and values are treated very much the same. A value has a type. A function also has a type, which happens to be composed of its argument type and its result type. I used the word composed intentionally here. Sometimes functional programmers even think of values as functions that return a result without requiring any argument. In functional programming languages, functions can take other functions as arguments and return functions as results. These are sometimes referred to as higher order functions. I'll use parentheses to refer to arguments and results that are functions. So, is a function whose argument is a function mapping w to x and whose result is a function mapping y to z. In software development, we often find ourselves writing functions that turn out to be identical in operation, but they happen to take arguments of different types or return values of different types. For example, you might write a function that takes a list of integers and returns their average. You might write another function that takes a list of floating point numbers and returns their average. You wouldn't be surprised to find that these two functions are almost identical. Good software developers always seek ways to eliminate duplication, and functional programming languages help them by letting them in a way make the type itself an argument of the function. Of course, this is done at the time of definition, whereas at runtime, the functions will receive specific types. For example, suppose we fire up a text editor and write, in our functional programming language, two functions, m sub I, returning the mean of a list of integers, and m sub f, returning the mean of a list of floating point numbers. These functions perform the identical operations on their argument, even though the types are different. We'd like to be able to define m sub a mapping a to float, where a represents any type. At the time of definition, we specify a as a type variable in the function. At runtime, some value of an actual type will get passed to the function. Similarly, we might have a function f mapping a to a, which maps a value of some type to a value of the same type. Such functions are called parameterized type functions. Parameterized types provide a way of grouping functions and defining them in ways that are identical except for a type. I said earlier that functional programming languages blur the distinction between values and functions. Parameterized type functions go further by blurring the distinction between values and types. I'll write f:(a right arrow a to mean a function that maps an argument of any type to a result of the same type. I'll write f:(a right arrow b to mean a function that maps an argument of any type to a result of any type, even the same type. A parameterized type constructor is simply a parameterized type function that maps a value of some type to a composite of that type. Such a function maps a value of type A to a value of type M composing A. The composite type disjoins or conjoins that type. We don't know much else about the composite type from what's said here. For example, you might have a function that takes an integer and returns a list containing that integer, or that takes a string and returns a binary tree containing that string. It's also possible to have a parameterized type function that maps a value of some type to a composite of a different type. For example, you might have a function that takes an integer and returns a list containing a floating point number, or that takes a string and returns a binary tree of characters. Let's see if we can assemble a monad from what we know about functional programming languages. A functional programming language gives us a set of simple and composite types. The composite types can even be defined in terms of themselves. We'll use this as the set of abstract objects for our category. A function maps an argument of some type to a result of some type. So functions can play the part of morphisms on the objects in our category. A function can map an argument of some type to a result of the same type. So such functions can provide identity morphisms on objects in our category. A functional programming language allows two functions to be composed. If you have f sub 1, which maps x to y, and f sub 2, which maps y to z, then a composed function, f sub 2 circle f sub 1, mapping x to z, can simply call f sub 1 on its argument, producing an intermediate result. The composite can call f sub 2 on the intermediate result to produce a result of type z. The right set of functions will be composable associatively. Composite functions can be defined in terms of functions mapping A to A and other composite functions. So we have everything we need to assemble a category in a programming language. Remember that for a functor, we need two things: an object morphism, a morphism or function mapping every object or type to another object or type, and a morphism, a morphism or function mapping every morphism or function to another morphism or function. A parameterized type constructor mapping A to M sub B provides a function from every type in the language to another type. This can be an object morphism. If the result type happens to be a composite of the given type, A mapping M sub A, the constructor also provides a function from every type to itself. This can be an object morphism for an identity functor. To complete an endofunctor, we also need a morphism. In a functional programming language, this requirement is satisfied by a higher order function called functor map or fmap. How would fmap operate? Imagine calling it with a function mapping A to B. Fmap would define a new function mapping M sub A to M sub B. The new function would accept an argument of type m sub a. It would decompose the a value out of that argument, run f on it to generate a b value, compose that into an m sub b type value, and return it. The morphism for an identity functor is trivial. We just need a higher order function fmap that simply returns its argument. At this point, we have everything we need to define an endofunctor and an identity functor. What would it mean to compose two endofunctors? Our first endofunctor would have two functions, an object morphism and a morphism. Our second endofunctor would also have two functions, an object morphism and a morphism. We would want a composite of these two to have two functions. The composite endofunctor's object morphism could execute the function a mapping m sub b, decompose the b value out of it, execute the function mapping b to m sub c, and return the result. The composite endofunctor's fmap would operate just like I said before. It would accept an argument mapping a to c. It would define a new function mapping m sub a to m sub c. The new function would accept an argument of type m sub a. It would decompose the a value out of that argument, run f on it to generate a c value, compose that into an m sub c value, and return it. If this composition is associative, then we would have a monad. This video described how we might build a monad in a functional programming language. I hope you got a sense that the repeated application of certain abstract patterns let you express complex structures simply. The next video will get into how category theory and monads have influenced functional programming languages and why they are important.